Hello everyone, welcome back to our Lee County Library Science Club. It's great to have you with us once again. And this time, you're in for a special treat. Our event today is a part of the North Carolina Science Festival, and specifically their Star Party. Now the Star Party is actually taking place tomorrow night, so some of the things we talk about today, you can go and put into practice tomorrow night when you participate in the Star Party with the rest of the North Carolina Science Festival. Now the theme of this year's Star Party is the Moon and Mars. And they specifically picked those because they're two of the easiest things to see in the night sky with your naked eye. Meaning, no telescope, no binoculars, just with your own eyes you can see the Moon and you can see Mars. And the reason you can see those two things, they are the closest celestial, or in the sky, in space, they're the closest celestial bodies to the Earth. The Moon especially, obviously, right? We know the Moon is close to Earth. It revolves around the Earth. Mars is the planet with the closest orbit to the Earth, but Mars is not always close to Earth. Sometimes, when our orbits are not coinciding, we're actually really far apart. So, in talking about all of that, I use the word revolve and orbit. But what do those things mean? Well, revolve simply means to go around. This baseball, if I put my arm out and I spin the baseball around, it is revolving around my shoulder, right? It keeps going around my shoulder. And that's what happens with the planets going around the sun and our moon going around Earth. And when they continue to revolve around that thing in a set pattern that repeats over and over and over again, in the case of our solar system, millions of years, it becomes what we call an orbit. Now, what actually causes an orbit? Well, as we have talked about before, one of the fundamental forces and properties of our universe is the concept of gravity, right? Things fall down. And we talked before about how larger mass creates a larger gravitational pull, about the distance from that mass affects how strong that pull is, right? The farther you get from Earth, the less it will actually pull on you, which is why when our astronauts go up in space, they seem weightless, right? And they're almost weightless. They still are being pulled a tiny bit by the Earth, but it's not something they can really even notice. But if, as we've talked about, larger mass things have larger gravity, well, why when two things like planets or the Earth and the Moon, when they get close to each other, why doesn't their gravity just pull them together and they smash together? Well, that would be really bad for us, right? Number one. But it's also because in space, there is almost zero what we call friction. Now, friction is another kind of fundamental force of physics in our universe, and that is the force of resistance, right? If I put my hand on this table and I push, I have to actually push to be able to move across the table, right? And that's because there's friction between my hand and the table. And we've talked about that before as well when we made the phone books stick together, right? We couldn't pull it apart because the friction force was so strong. Well, on Earth, there is a lot of friction, right? All the solid objects are hard to go against, but even in the air, if I'm throwing this baseball up and down, it's experiencing friction due to the air molecules around it. Well, up in space, there are almost no particles whatsoever. I mean, if maybe there are some air molecules, they're very, very spread out. There are obviously some solid materials, and those kind of come together into things like asteroids, and we actually sometimes see them fall to Earth in the form of meteors or meteorites, right? But those are kind of really rare. And so if something is traveling through space, it's experiencing almost no friction whatsoever. And so if there's no friction, well, is it going to slow down? Generally not, right? If something doesn't have any force pushing against it as it travels, well, then it's just going to keep going that same speed. Or if there's still force acting on it, it's actually going to keep moving faster and faster. And so if you have things, large celestial bodies like a planet or a moon, and it is traveling through space, it doesn't have anything to slow it down. So if you have two large things in space moving at a high enough velocity, when they get near each other, well, they still want to keep moving the direction they were going, right? But they also pull against each other. So they'll come, and they'll want to keep moving, and they'll pull against each other, and they'll start to pull like this, right? And so they're still moving as fast as they were, but they're also being pulled by that other object. Let's do a little bit of demonstration of this. Ready? So one way to understand gravity and orbits was actually proposed by none other than Albert Einstein. And he had us picture gravity as affecting what he called space-time. And so what we see here is sort of a depiction of how that might happen. I've just got some stretchy fabric stretched over a large barrel here. The coffee can in the middle is, say, maybe our sun, right? A large celestial body at the center of, in this case, our solar system. And as you can see, it's pressing down pretty heavily on our fabric, isn't it? And our fabric represents space-time. So it creates a depression in space-time that when other objects, like this baseball, when they might be traveling along space-time and they get near it, they might get caught in that depression. And as you can see, they get drawn in to the middle. Now, for us, again, we talked about there's a lot of friction in this, right? This fabric is not all that smooth, so there's friction there. There's friction in the air as it's traveling. And so we can't actually create a stable orbit. But you can see how one might start, right? As something spins around and revolves around, you see it get caught in the orbit of our larger object. And that is what happens in space. And it's interesting, if we now take a golf ball instead of that baseball, does it take? It takes a little longer to settle down into the middle there, doesn't it? Because as we talked about, larger objects experience a larger gravitational pull. So this baseball is pulled harder towards the coffee can than this golf ball. And it's also interesting, this still creates a little bit of a depression on its own, right? So if we took this baseball and these golf balls and put them in there all at the same time, well, they kind of move around each other as they go around the coffee can, don't they? That is what happens with moons. Let's try with just one this time. So our moon is this golf ball, and we are the Earth traveling around the sun. And as they travel together, you can see that golf ball kind of moves with and around the baseball, doesn't it? Now again, there's no friction up in space, so rather than coming to settle in the middle, this baseball would continue traveling around that ring forever. And the golf ball would follow it because it's drawn by its gravity. So what's actually happening in our solar system is we have planets moving of different sizes and at different speeds, all traveling around the sun at the same time. And as you can see, if there was friction in space, we'd all be in a lot of trouble, wouldn't we? Because all the planets would crash together and crash into the sun. So we're thankful that there's no friction out in space, and we get to just continue in our orbit without crashing into anything. Now the other thing we talked about that affects this is how fast they're moving, right? So if I put this baseball in really slow, well, it's drawn very quickly into the middle, isn't it? However, if I give it a little bit more speed, it gets to go around a couple more times and take a little bit longer to get to the middle. And let's see with the golf balls, since they're all about the same size, if I give them different speeds, what happens? So let's do a slow one, a little bit faster, a lot faster. You can see they all took different routes and different amounts of time to get to the middle. So again, the size and the speed of these celestial bodies affects how they experience an orbit. So now that we've seen what orbits might look like and what causes them, well, let's see about how they affect what we experience every day. So as we know, the Earth is revolving around the sun, right? But at the same time, the moon is revolving around the Earth. And this phenomenon of the Earth traveling around the sun and the moon traveling around the Earth, this causes what we know as the phases of the moon. And this comes from the moon being in different positions relative to the Earth and the sun's light shining on it at different angles. Let me show you what we're talking about. So let's pretend again that my baseball here is the moon and my flashlight is the sun. Now as you're seeing it right now, you're only seeing about half the baseball being lit up, right? So this is where the moon is kind of next to the Earth in its revolution. When, let's say, the sun is behind the Earth in relation to the moon, that's when we get a full moon, right? So you have the Earth, the moon on one side, and the sun on the other. We get to see the sun's light reflected directly back from the face of the moon. Now, when the moon is on the other side of the Earth, again, we see about a half moon, but from the other side this time. What happens if we have our moon and it is between the Earth and the sun? Well, you don't really see it get brighter at all, do you? In fact, when it's at an angle to the sun and the Earth, it becomes really hard to see the moon, doesn't it? And this is what we experience as a new moon. The moon traveling around the Earth, and the way its light gets reflected back to us is what causes the phases of the moon. So as you can see, I know the baseball is not moving right now, but let's pretend that our camera is moving with the moon as it travels around the Earth. And so our light from our sun shines at different angles, doesn't it? And that is what causes the phases of the moon. So now that you understand what causes the phases of the moon and how the movement of the moon, the Earth, and the sun interacts with each other to affect what we see, let's do a fun little activity to see what the phases of the moon look like. Now, in order to do this with me, you can actually come down to the library and pick up one of our science kits that is the Oreo moon phases. However, if you don't want to do that, you can still participate at home. All you need are some Oreos and a spoon, and if you get one from the library, we have this handy moon phase demonstration sheet and some instructions. However, you can always just do this on your own with the Oreos and the spoon and any piece of paper you'd like. So, let's take a closer look. Now, as you can see, we have our moon phases, and they are labeled new moon, waxing crescent, first quarter, waxing gibbous, full moon, waning gibbous, last quarter, waning crescent. Now waxing simply means increasing or getting bigger. Waning means getting smaller. And crescent and gibbous are shapes. Crescent is kind of that typical man in the moon shape that we've seen. A gibbous is kind of the opposite of that, where it's almost a circle, but there's like a piece sliced off of it. So we are going to use our Oreos to create these shapes. Now the first thing you're going to do is take your Oreos and twist them so that they come apart. Try to be kind of gentle so you can get as much of the cream all together on one side as possible. Now, this one's pretty easy, right? We see all of the white. So that is what? That's right, that is our full moon. And this side, well, it has a tiny bit of white on there. Let's scrape that off with our spoon. Okay? There's not any white on there at all. So this becomes what? That is our new moon, where it's just dark. We don't see any light at all. Now just a quick tip. I know it's really tempting, but don't eat any of your Oreos until we're all done. I promise at the end you can eat them. But for now, try to restrain yourself. So next, we're going to take another Oreo. Okay, separate it like that. Now, this up here is the new moon, so let's take our dark one and put it next to it. And let's take our light side and put it next to the other one. But, in order to get, as we called it, the gibbous shape, or the crescent shape, we need to take some of our cream from here and put it up here, right? But which side will we take from? Well, the moon in its phases changes or seems to grow from right to left when you're looking at it from where we live in the northern hemisphere. So if we have our new moon here, and we want this to be a waxing crescent, then the crescent needs to be on the right-hand side of this, right? So if we want a crescent on this side, then we need to take part of this side off. And this is where we want to have a spoon so we can kind of cut our crescent off of that side and put it on the other side. You see that? So now we had our new moon here, which is when the moon is between the earth and the sun, and we don't see any reflection at all. Now it's starting to travel back around, and we see it start to grow. Let's do our next one. Now again, let's separate them carefully. And we'll put our, ooh, didn't do a great job that time. Well, we'll put one side on the top, one side on the bottom. Now this one, it says first quarter and last quarter. So actually, we need that on that side. What does it mean, first quarter and last quarter? Well, it's talking about the full phase of the moon, from new moon to full moon, and back again to new moon. So the quarter is of the cycle, but what actually happens is it looks like to us a half moon. So we're going to be a little bit careful here, and we're going to take this part off and try to put it over here, put it in the middle there, and then we'll take this part off of here and put it right over here. So now we have our right-sided half moon for the first quarter when it's waxing or getting bigger, and we have our left-sided half moon for the last quarter when it's waning or getting smaller. So the last thing we have to do is our waxing gibbous and waning crescent. Oh wow, look at that. As I separated it, it did it all by itself, didn't it? So we've got a crescent here, and we've got a gibbous here. And so once again, we can see we start with the new moon when the moon is between the Earth and the Sun. As the moon starts to revolve around the Earth, we see more of the Sun's light get reflected in our waxing crescent. And then once the moon is pretty much even with the Earth, we see the sunlight being reflected off of half the moon in our first quarter. As it moves further, we get our waxing gibbous. Once the moon is on the opposite side of the Earth, so now the Earth is between the moon and the sun, we see the sun fully reflected off the moon and we get a full moon. And then it continues that circle around and it starts to get smaller. It starts to wane. We get a waning gibbous. It wanes a little more into our last quarter, or our other half moon. And then finally it moves back towards the sun again, and we get our waning crescent just before it goes back again to our new moon. Now this is a very fun and tasty way for you to see what the moon's phases look like. But it's not nearly as cool as watching the actual phases of the moon. So why don't you go ahead and join the Star Party tomorrow night, go outside, and see what the moon is. Talk with your parents, figure out what phase the moon is in, and maybe you can share that with us on our Facebook page or on our Instagram page. Right, maybe you can take a picture, put it up on Instagram, and tell us what you think the moon phase is. Is it a crescent? Is it a quarter? Is it a gibbous? Is it waxing or waning? Tell us what's going on. And in the meantime, enjoy the Star Party with all the rest of North Carolina. Thank you so much for joining us for this North Carolina Science Festival event. It's an honor to be a part of the Star Party. I hope you guys enjoy it. For more information about orbits and planets and how things move, please check out the Moorhead Planetarium in Chapel Hill. You can find out more about them by visiting their website at moorheadplanetarium.org. And if you're interested in more Science Festival events, well, this is just one of hundreds that are taking place across the state. And many of them are virtual, just like this. So go on to ncscifest.org or ncsciencefestival.org and find something you're interested in. We'll see you next time. Bye.